Hi there! In the previous video, I introduced the concept of federated satellite systems in the context of opportunities for the new space industry. I gave an overview of distributed satellite systems and on the role of digitalization of space systems in general. We looked at the idea of federated satellite systems, or FSS, and we talked about its applications in the domain of Earth observation and space telecommunications. Lastly, I briefly talk about the technical challenges and benefits involved. In this video, I'm going to go further on this topic, as it is very rich and it offers much opportunities for ideas for the new space industry. I'm going to talk about the experience of the research group that I lead at Skoltech in selected research projects related to the topic of federated satellite systems. First, I'm going to give a detailed overview of one of our first works in FSS, that is on the business case assessment of the idea through an integrated technical economical analysis. Second, I'm going to overview a European research project where our research team was a participant that explored the use of FSS in Earth observation, and specifically to complement the European Copernicus satellite infrastructure. Third, I am going to talk about one of the potential concepts enabled by FSS, that is cloud computing in space, and its realization through the establishment of an Earth orbiting support system. Fourth, I am going to briefly comment on policies that are useful to operate federated satellite systems in space. In particular, I'm going to overview the analysis we have done in using reverse auctioning systems to regulate the operations of FSS. Fifth, I'm going to overview the problem of cybersecurity in FSS, and in particular the issues of data security and confidentiality, with our proposal on the potential mechanisms on how to approach them. Sixth and last, I'm going to talk about the creation and operations of virtual satellite missions, or in other words, the dematerialization of space systems for the benefit of end users and increase the scalability of space services. Let's get started! First, let us start looking at the key questions to determine when and why federated satellite system concepts make sense and for which applications. Given the commercial nature by which this all started, it makes sense to do proper technical diligence to determine the business conditions under which federated satellite systems result in being commercially viable. Let us consider federated satellite systems as an asset trading market, where orbital resources such as bandwidth, processing power, and so on are the commodities that are being traded. Trades occur between customers and suppliers of resources. A federated spacecraft can then be a customer, a supplier, or both during operations. Let us consider, for example, the scenario where the International Space Station is taken as a potential supplier of resources, and let us consider all spacecraft around Earth orbit as potential customers. This is indeed a fictional scenario, as there are many engineering reasons why existing satellites cannot engage right away in federated operations. For the moment, let us focus ourselves on the evaluation of the business case. The chart on the left shows the population of active satellites orbiting around the Earth circa 2013. This chart comes from the paper that Dr. Lluch and myself published a few years ago. The link to the full paper is provided in the description of the video. Based on publicly available data, we mapped active spacecraft according to the orbital altitude, shown on the horizontal axis of the chart, and according to their inclination, shown here on the vertical axis. The chart clearly shows the three big families of spacecraft operating in Earth orbit. On the left, we have the satellites in low Earth orbit, on the middle, the satellites in medium Earth orbit, and on the right, the satellites in geostationary orbit, as you would expect. We made assumptions on data volume generated by each satellite according to its mission type and instrument, be it Earth observation, Earth science, navigation, telecommunications, and others, with an estimated their needs for resources such as processing power, downlink bandwidth, and so on. The goal was to understand whether this potential market, considered as the best possible case, would economically make sense for a provider of federated services in orbit. We then assumed a single supplier operating out of the International Space Station, that here in the chart is shown by the little station icon. On this basis, we assumed we would mount an antenna farm or an optical receiving station on board the ISS and started offering cloud services of data downlink and processing to in-space customers. As for pricing, we assumed an adaptive pricing policy where we would consider the equivalent opportunity cost should a customer carry the mission entirely on their spacecraft. We would then run a cost-benefit analysis essentially, modeling the link budget and considering orbital dynamics constraints. At the end, we produced the net present value analysis of the service, so effectively a financial valuation that projects the operations of the service over a number of years. The results were quite enlightening, in fact. We quickly discovered that from the ISS, we would focus on customers in low Earth orbit. The other orbits would lead to non-economical services. As for LEO, we estimated the net present value for a number of representative RF frequencies and in the case of optical communications as well. The assumption was indeed that all customers were able to communicate at that given frequency or technology. This is indeed a strong assumption because of spectrum allocation and interference-related issues. One of the approaches to mitigate these issues is indeed the use of optical communications, which we also considered. So imagine running a cloud service provider out of the ISS and customer satellites calling in for services for data processing, AI, fast downlink, and so on. This is what this is all about. Given all the significant technical challenges to overcome, our technical financial analysis unveiled significant economic opportunities, measured by positive net present value for running such cloud services in space. Provided now that FSS holds promise for economic potential, let us see what kind of commercial applications could we put in place using federated concepts. In the context of Earth observation, our research team at Skoltech participated in the ONION project, co-funded under the Horizon 2020 European Research Programme. Constellation architectures are the most well understood and more studied among distributed satellite systems. ONION identified and characterized solutions to meet emerging needs in Earth observation. We explored federated satellite system solutions and proposed the evolution of satellite constellations for Earth observation as enhanced by federated services. One of the cases where we demonstrated the approach was a use case focusing on Arctic and subarctic communities for marine weather forecast. We investigated synergies between the European Copernicus Earth observation infrastructure and potential enhancement by federated systems to achieve high temporal resolution and low latency time to download data on the ground. In the specific use case, for example, we identified the system architecture made of 8 small nodes, CubeSats carrying GNSS reflectometry instruments, and 8 heavy nodes, 600 kilo class satellites carrying a synthetic aperture radar and an optical imager. The satellites will work in a federation through inter-satellite links to achieve those common goals in observation and data downlink. ONION described an end-to-end example on how large industry organizations can effectively work with new space startups and academia to drive innovation in the space sector. It is a great example of innovation that opened opportunities for anyone in the community to contribute and new ideas for new space startups. Another application area for federated satellite systems is in space telecommunications. In a study in collaboration with the University of Rome La Sapienza, we envisioned a cloud computing service operating in space and called it EOS, which stands for Earth Orbiting Support System. In our joint work for EOS, we proposed a methodology to explore the trace space of EOS and identify the most promising system architectures for more detailed design exploration. We considered 2 case studies where such cloud infrastructure would serve between 30 and 100 customers respectively, and looked at potential markets in the exploration, Earth observation, science, and small satellite domains. Our research has shown increasing performance of such constellations by increasing the number of participating satellites or nodes. On the other hand, we identified non-obvious trends in other design variables such as optimal orbital altitude, number of satellites per plane, and number of orbital planes. Startups conceiving constellations for cloud data secure storage are now reality. I can definitely foresee other space-as-a-service systems coming to light in the near to midterm future. Once you establish this paradigm of federated satellite services, the opportunities to build on it are essentially limitless. One of the key questions to consider, for example, is how to regulate the operations and transactions in such a market. One possible approach is to think of dynamic pricing policies pretty much similar to what is done in the online advertising industry. The mechanism I'm talking about is called reverse auctioning. In reverse auctions, multiple sellers of a given service compete, essentially underbidding each other to obtain a business from a certain buyer. With Udrivov Pica, we analyzed the case of inter-satellite links operated using reverse auctioning mechanisms. We modeled such operations for a satellite federation and characterized the elasticity of such markets. Elasticity is measured by the marginal changes in average pricing as a function of available suppliers of in-orbit networking. In this work, we measured the relevance of key parameters in regulating pricing for federated operations, such as the number of suppliers able to operate around the bidder, the number of customers able to operate around the bidder, and the number of hops required for any given data path to reach the ground. In our simulations, we recreated all typical market conditions, including oligopoly, competitive markets, and saturated markets. The work concluded drawing recommendations for future operations should reverse bidding be chosen as a mode of operation of commercial satellite federations. Check out the paper linked in the description below for more details on this approach and how it could be used to regulate operations of future satellite federates. Federated transactions would certainly have to be recorded somewhere. At the time, we thought about the use of in-space blockchain ledgers. Blockchain would bring several advantages in the operations of a satellite federation, including traceability of transactions and inherent security. On the other hand, several technical challenges remain to be solved to implement such an approach. First and foremost, the technical burden of the proof of work. Blockchains to operate securely require significant processing power, which is usually a scarce resource in space operations. We should expect then the operations of power-efficient blockchains, which come as a result of sophisticated schemes for trust making in blockchain nodes and trust propagation. The complexity associated with orbital dynamics in such an implementation should be considered as well. This is indeed an area of opportunity for research and for development by a new space startup. Another area of interest in federated satellite systems is certainly cybersecurity of FSS operations. Imagine you have a commercial satellite federation operating in orbit, and suddenly you have a malicious supplier or a malicious customer in the federation. This would indeed pose serious problems right away. The malicious node may indeed breach security, integrity, or confidentiality of all data transactions in the network. A possible approach to mitigate this risk is the adoption of a public key infrastructure such as PGP. With Olga von Maurich, we studied such an implementation and simulated its performance on flat-sat hardware. Essentially, we imagine having a trusted organization generating and distributed private and public keys for encrypted communication in satellite federations, and estimated the computational overhead associated with such mechanisms. In our work, we have noticed that traditional encryption methods induce acceptable computational overheads for moderate data volumes, say in the order of hundreds of megabytes, but they get indeed more expensive for larger volumes of data. The work sets a framework then to evaluate those overheads beforehand and make decisions on trade-offs between the desired levels of security and the infrastructure requirements needed to sustain the increased data volume. We published this work in a paper titled Data Authentication, Integrity and Confidentiality Mechanisms for Federated Satellite Systems. As other research works described before, you can access it through the link you can find in the description of this video. Now to set out the grounds for FSS and explore some of the key issues in its value proposition, operations and security, let us have a closer look on the application side. What could you do once you have a federation up and running in orbit? One of the immediate applications one could think of is to deliver direct applications to the end user. This is the core idea behind virtual satellite missions, or VSM in short. A VSM is a satellite mission that is designed and operated without the need for building and launching any satellite at all. A VSM is put together by coordinating resources in a satellite federation. So for instance, a user interested in Earth observation capability could pull out instrument time from spacecraft A, data processing from satellite B, storage if needed on satellite C, and downlink from satellite D and satellite E. What are the advantages of such an approach? To start with, End users could create missions as a service for limited periods of time, such as few hours, if not few days. The barriers of entry to the utilization of space assets would be significantly lowered with VSMs. Users would be able to acquire data exactly the way they need it, combining observations as needed, which is not really something that is possible today without operating a proprietary mission. Another obvious advantage is the improved utilization efficiency by participating spacecraft that essentially operate their spare capacity. How would these virtual missions operate, and how would their concept of operations look like? Well, we explored this issue in a paper in 2015 with Ripsim and Matevosyan. We envisioned a VSM operations center on the ground, collecting user requests and scheduling the coordination of resources in all participating federations. In our paper, we simulated the operations of a notional VSM and estimated performance bounds in terms of operational efficiency. We discuss all the results in the paper, which I invite you to read. Check out the link to the paper on virtual satellite missions in the description below the video. Okay, we covered a lot of ground today. We went deeper into the topic of federated satellite systems and had a closer look to selected research topics. We overviewed the business case assessment of FSS and analyzed why we think such a concept makes sense, first of all, to develop. We looked at potential commercial implementation in a dedicated cloud constellation system, which we called Earth Orbiting Support System. We then went on and examined the potential mechanism to operate satellite federations, looking at reverse auctioning pricing policies. And finally, we outlined the idea of virtual satellite missions and how this could represent an opportunity for development of new space services to the end users. We are not finished yet with this topic. I would like to give you a deeper insight on the technical aspects of federated satellite systems. In the next video, we're going to talk about space internetworking, which is an essential aspect in the operations of federated satellite systems. For this video, we will have a special guest speaking, Joan Ruiz de Azua from the Universitat Politécnica de Catalunya. Stay tuned. Thank you very much for your attention. Goodbye.